This first chapter defines an option's delta from a number of different perspectives and explains how delta changes under different market conditions and different contractual terms for the option. Using our old worksheet GK, we analyze the price movements of calls and puts as we move spot up and down to various levels. We remind you that we are pricing 6-month European calls and puts with a strike of 150 when both sterling and dollar interest rates are 5% and when vol is 10%. So for example, if spot drops to 130, the call seems to be worth 0.0008, while the put is worth 0.1958, and so on. This table lays out results for 6 different levels of the spot for both the call and the put. We make a number of observations about the price patterns of calls that you see in this table. At 130, the call is deep out of the money and is worth very little, specifically $0.0008, given how unlikely it is that it will be exercised on the expiration date. At 170, the call is deep in the money and is worth a great deal, specifically 0.1968. In fact, is almost exactly equal to the call's intrinsic value, which we define as the forward minus the strike. And at 150, the call is at the money and is of course worth something in between these two extremes. Turning now to how the premium changes as the spot changes. You will note that when we increased spot by 1 cent exactly in the 3 states of the call option, the out-of-the-money call rose by only 0.0002, the at-the-money call rose by 0.0050, and the in-the-money call rose by 0.0094, substantially more than the other two. You may intuit that the out-of-the-money call reacts very little to a 1 cent spot movement. The at-the-money call gains exactly half a cent for this 1 cent spot increase, while the in-the-money call gains almost an entire cent. This ratio of the two price movements is known as the option's delta, which we define therefore as the ratio of the change in the option's premium for a 1 cent increase in the spot. Note that the decision to define delta relative to a 1 cent movement in the spot is somewhat arbitrary. We could have used 0.1 cent or 5 cents, but as we will see, a small movement in spot is certainly preferable to a large one for purposes of this definition. Based on what we saw above, we are tempted to say that the delta of a deep in the money call, deep out of the money call is close to 0. For a deep in the money call, it is close to 1. And for an at the money call, it is close to 0.5. These relationships can be formally shown to be more or less correct, and to become more accurate still as the time to maturity approaches 0, and especially if volatility is low or moderate. They are in fact less accurate for long-dated options and/or in a high vol environment. You should click pause and, using spreadsheet GK, confirm this to your satisfaction. The graph you now see on the right shows the calls delta moving from close to 0 on the left to almost 1 on the right, as the spot gradually rises from 120, 130 to around 170, 180. For puts, the following can be observed from our table. At 170, the put is deep out of the money and is worth very little, given how unlikely it is that it will be exercised on the expiration date. At 130, the put is deep in the money and is worth a great deal. In fact, is almost exactly equal to the put's intrinsic value, which we define as the strike minus the forward. And at 150, the put is at the money and is of course worth something in between these two extremes. The results in the table also appear to indicate that the delta of a deep out of the money put is close to 0. For a deep in the money put, it is close to -1, and for an at the money put, it is close to -0.5, all of which again can be formally shown to be more or less correct and to become more accurate as the time to maturity approaches 0 and volatility is low or moderate, and less accurate for long-dated options in a high-vol environment. Note our use of the negative sign for the put's delta, which is technically correct since increases in spot result in drops in the put's value and vice versa. The graph you now see on the right shows the put's delta moving from close to 0 on the right to almost -1 on the left, as the spot diminishes gradually from 170 or 180 to around 130 or 120. The exact mathematical definition of an options delta is given by this formula here, which means the ratio of the change in the options price or premium as the spot increases by a very, very small amount, much smaller even than 1 cent. The use of the curly letter D in mathematics indicates that the other variables in the formula, namely the strike, the two interest rates, the volatility, and the tenor, must be held constant for purposes of this definition. Of course, this never happens in practice, but since we have a closed-end formula for the call and puts premium under our model GK, it turns out we can also derive a closed-end formula for their delta, which permits us to calculate it exactly at any level of the spot. The formula for delta has been added into our previous worksheet GK, which has been renamed in a separate worksheet GK2, and to which we will turn shortly. It should be apparent at this point that if we plot the graph of the call's value versus spot, we get the shape appearing on this slide. Note first the very low values on the left, where the call is deep out of the money, such as this point here, where the spot is 1.3. The rising values also as spot increases. And finally, and very importantly, how the value of the call approaches the intrinsic value, shown in this graph by this diagonal in blue, when the call becomes deep in the money on the right. Visually, delta is the slope or tangent or gradient, as we say in math, of this graph. That slope or gradient is almost 0 when you're deep out of the money, almost 1 when you're deep in the money, and somewhere in between for those intermediate states, including when the option is at the money, indicated by this green point right here. In fact, the slope for the at the money call is almost exactly 0.5 here, although this may be difficult for you to see precisely on this graph. This delta of 0.5 means that as you move 2 units along the x-axis towards the right, you would move half as much, i.e. by 1 unit, along the y-axis. The graph for the put appears next, confirming once again the very low values, this time on the right, when the put is deep out of the money. The rising values as the spot decreases and you start moving to the left. And finally, once again, a value that approaches the intrinsic value, shown once again in this graph by the blue diagonal, as the put becomes deep in the money on the left. Once again, the visual interpretation of delta for the put is the slope or tangent of the pink graph. Almost 0 when on the extreme right, almost -1, corresponding to a 45-degree angle of the blue diagonal on the extreme left when you're deep in the money, and somewhere in between for intermediate states, including when the put is exactly at the money. And at that point, once again, the slope would be almost exactly minus 0.5, which means that as you move 2 units along the x-axis, but this time going down towards the left, you move half as much, i.e. by 1 unit, up along the y-axis. It is common to state an option's delta as a percentage, which is of course really the same thing as a decimal. But please be careful about one thing if you adopt this convention. The percentage that represents delta is the change in the option's value in units of currency divided by a 1 unit increase in the spot. It is not the ratio of the change in the option's value to its initial value prior to the increase in the spot. To illustrate, consider the at the money call again, whose value increased from 0.0388 to 0.0438, so roughly half a cent, when spot increased by 1 cent. If you divide half a cent by the original price of 0.0388, you would get a percentage shown in the calculation on the right equal to 12.89%, which is categorically not the call's delta, and in fact significantly understates it. This example may be easy to remember for the at-the-money call, since you knew to expect the delta close to 50%, as shown in the calculation on the left. But consider for a second the deep out-of-the-money call. Here, the call's value increased from 0.0008 to 0.001 when spot increased by 1 cent, which is consistent with a 2% delta. The erroneous definition of delta would generate, as you can see on the right, a delta of 25%, which completely overstates the real delta. The last definition of delta is one that has never in fact been quite correct, but is so user-friendly that many practitioners rely on it a great deal. We can think of delta as the probability that the option will be in the money at expiration, i.e. that it will be exercised. In fact, it can be shown mathematically that this probability is strictly equal to the n d2 term in the GK formula, which, by the way, is programmed in a hidden cell in worksheet GK. It turns out in most cases these two quantities, i.e. n of d2 and delta, are very close in value. So the inaccurate interpretation of delta as the option's probability of being in the money at expiration has become commonplace despite its imprecision. You can see how intuitively appealing this interpretation is. We know that a deep out of the money option, I beg your pardon, has a very low probability of exercise at expiration, so its delta must be close to 0. We also know that a deep in the money option is almost certain of expiring in the money, especially if volatility is moderate. So its delta must be close to 1 under this definition, which again you know is true. And finally, we know that an option that is at the money forward would appear fairly reasonably to have a 50-50 probability of expiring in the money by its maturity date, given in a way that it is right on the cusp, so to speak. Therefore, its delta of 50% is again confirmed via this intuition. Note that when applying this imprecise interpretation to puts, one additional inaccuracy creeps in, since probabilities are always positive, while put deltas are by definition negative, as we explained previously. One last property of delta is how it changes as the option approaches expiration, assuming all other factors remain constant as usual. In this worksheet GK2, we begin with a 1-year at-the-money call and gradually reduce its tenor by, let's say, 1/10 of a year at a time. We see the initial call delta of 0.4946, which is already close enough to 0.5, gradually rise, initially, ever so slowly towards 0.5, then at some point actually exceeding ever so slightly 0.5, continuing to rise above it very slightly for reasons not worth discussing here, and at all times essentially remaining very, very close to 0.5. We are therefore able to confirm with some confidence the very frequently stated rule that when an option is at the money forward, of course, its delta would be close to 0.5, irrespective of its tenor. You should treat this rule with some caution, however. If you either lengthen the option's tenor significantly, or if you raise the vol significantly, you will find the delta of the at-the-money option will begin to deviate materially from 0.5. For example, if we assume a 5-year tenor for the option, delta drops to 0.4241, and we haven't even changed vol yet. By the same token, if we put the tenor back to, let's say, half a year, but assume a 50% vol, which is probably unheard of for most currencies, but not impossible for some equities and commodities, this time we see the delta actually exceeding 0.5 by quite a bit. However, since most FX options are relatively short-dated, between 0 and 1 year, we really can say that in general, the delta for an at-the-money option in FX is just about 0.5. The in-the-money call, which we will visualize by changing spot to 1.7, of course, behaves quite differently. This time let's start with a tenor of 3 years and observe what happens to the delta. Initially, this delta appears to be around 68% and begins rising as we shorten the tenor, which we will do in increments of half a year. So at a 2.5-year tenor, the delta is around 71, rising to 75 at 2 years, almost 80 at 1.5 year, 86 with 1 year left till expiration, 94 with half a year left, and virtually 1 with 1/10 of a year left just before expiration. This illustrates what is meant when people say that the moneyness of an option is relative. The 20-cent difference between the strike and the forward, really the best indication of how in the money or at the money or out of the money the option is. This 20-cent difference makes it almost certain that the option will expire in the money when we are talking of a very short remaining tenor. But it would be much less certain that this option would expire in the money when the option has, for example, 3 years to go, hence the significantly lower delta. The out-of-the-money call we talk about last, and we reflect this by inputting a spot of 1.3, and we will find that it behaves in exactly the reverse manner than the in-the-money call. At 3 years, the call delta is still 20%. There's still hope of bridging that 20-cent gap, climbing above that 1.5 over the next 3 years. But as time passes and the tenor declines, let's go a bit faster here, 2 years, we see the call's delta now at 0.16, and then at 1 year it has dropped to only about 0.08%, and finally just before expiration by 1/10 of a year, the call delta is already pretty much zero, at least to 4 decimal places of accuracy. In a sense, despite having been so far out of the money, this call still had, as we just mentioned, a reasonable amount of hope when there were 3 years left. But with much less time left, hope has disappeared, and the call has approached expiration while still being so far out of the money, and has essentially become completely hopeless. The graphs you see here summarize the above discussion and require little further explanation. Please note in red the delta for the out-of-the-money call at the bottom, in blue at the top the delta for the in-the-money call, and finally in the middle, in what looks more or less black, the delta for the at-the-money call, pretty much stuck around 0.5. We conclude this chapter with two closely related observations regarding delta. First, delta at any particular level of spot is different from delta at another level, even one that is close. This is why the formal definition of delta uses a very, very small change in the spot in the denominator of the ratio. By the time spot has moved by even this very small amount, the delta itself changes a little bit as well, so it is really critical to emphasize the varying nature of delta for changes in the spot. The second observation is that this rate of change of delta is itself far from constant across all levels of the spot, a reality that can be recognized in the graphs we saw earlier and which we reproduce here on the right, which plot the price of the call and of the put against spot, and the reality can be seen by the fact that the slope at any point, which is our delta, is not only changing, but is changing at different speeds depending on whether you are on the right, where the rate of change is slow, on the left, where it is slow as well, or finally closer to the middle, where it is pretty fast. We will explain shortly that this characteristic is known as gamma and plays a critical role in the risk management of options. This concludes Chapter 1.